All right, everyone. So welcome again to the New York Haskell meetup. Tonight we have a couple of great speakers, and the first one is going to be Hongbo Zhang with BuckleScript, a new JavaScript backend for OCaml. Give it up for Hongbo.
Good evening. Thank you for coming to the meetup. So today the topic is BuckleScript. I work in, can you hear me? So BuckleScript is a compiler open source by Bloomberg this January. It's a module, it's a readable JavaScript backend for the OCaml language. So previous there's a one called, also one that called JS OCaml. You give the OCaml bytecode to generate the whole JavaScript code. This is a new backend. It's a module-to-module compiler, which means compile one OCaml module to one JavaScript module, either ES6 module or CommonJS module or AMD.js module or Google Closure module. We currently support this module system. It means the one design goal of BuckleScript is to easily integrate with the existing JavaScript libraries. So it means you can easily call the OCaml libraries from JavaScript, or you can also call JavaScript library easily from the OCaml. And it also works with multiple front end. For example, the vanilla OCaml, you can use the vanilla OCaml syntax. If you don't like OCaml syntax, you can use other like the syntax polished for the JavaScript developer, like the reason. We'll talk more about later. So, I mean, we all know JavaScript is a very popular and very available platform. It's basically everywhere. You can develop the JavaScript applications, like even for the latest for the Apple TV. Also, like there's new standard called WebAssembly, which means you can do very low-level stuff and compile to the WebAssembly, and they will have a very good FFI for the JavaScript. So it means that this JavaScript platform will be even do more stuff like the low-level decoding and image processing in the future. It's a very attractive platform. That's why I want to compile OCaml to the JavaScript platform. Since this is a Haskell meetup, I mean, I assume you already know some basic of the type of ML like language. You already know the benefit of the static type system. And the thing with BuckleScript, the most cool thing with BuckleScript is OCaml. I mean, it's not a new language. I mean, it's already been developed for like almost 30 years from the Caml Lite, Caml Specialized, and the OCaml. I mean, they put a lot of effort in the compiler engineering. It's not like, I mean, not a graduate student project. It's being developed for multiple backends, including the AMD64, I mean, 32-bit, and a PowerPC, even like some exotic platform like Spark, the Solaris. They all provide a native backend for the OCaml. And recently, they also have the unikernel on top of the OCaml called the Mirage unikernel, which means you can use the OCaml language as a library OS. Then after you linking all the stuff, you can get a very small unikernel. And this compiler is also heavily used. It means it's used for real world, like in the high frequency training by some company like JavaScript. It's a high quality compiler. So the benefit bring by BuckleScript backend is a very high performance compiler. Either in compile time, I mean the compiler performance itself, and also the generated code is also running very fast. Also, we have a very spent a lot of time in designing the FFI, the foreign function interface, to make sure it works nicely with JavaScript. The other thing is, I mean, in most language, for most language to compile the JavaScript, you have to bring a very large runtime. But this is different in BuckleScript. Basically, you can write the very small OCaml self-contained OCaml code and compile to JavaScript code, which doesn't depend on OCaml runtime. Only when you need like the int64, this is not supported by JavaScript platform. In this case, we will link the int64 runtime support. And like for other like I mean MD5 hashing, this stuff which is not available in JavaScript standard library, then you have to link in the runtime. But you can write very self-contained JavaScript code, OCaml code compile to JavaScript without any dependency. And it's a separate compilation. It means compile OCaml module to JavaScript module. It's unlike like Scala.js, which means compile your whole applications into a single monolithic JavaScript code. It's just compile one OCaml module to one JavaScript module. And we support different module systems. Yeah, I mean, so there's a lot of effort recently to make OCaml language more friendly to JavaScript developers. For example, like the Facebook, they designed a new syntax for OCaml. It's called Reason. It's provide the JavaScript-like syntax. And they also know the front-end developer very much. I mean, it's basically the same people who develop the React.js and React Native. They create a new syntax called Reason. And the Reason will work with the BuckleScript together. You can write a Reason syntax, which is very like to JavaScript, and compile to JavaScript. So this is a very small example of the BuckleScript. The top is the OCaml code. The below is the JavaScript code. I mean, this is not the idiomatic OCaml code. It's just used for the comparison for against JavaScript code. So you see the top level is the OCaml code. We define a mutable intermap. And then we have for loop, adding the key value pair from 0 to 1 million. And then we have another for loop to confirm the key is indeed in the map. Then below is the generate JavaScript code. You can see side by side, you can see the code is very similar. So it's very easy to debug. It's unlike most transpiler. You generate very unreadable JavaScript code. It's very close. And the good thing is the performance is really, really good. We have a side-by-side example compared with the Facebook, the immutable.js library. Immutable.js is a very popular JavaScript library. It provides immutable collections. One is the immutable map. We do the same thing, adding the value. We have an empty map, and then adding the key value pairs from 0 to 1 million, and then verify if the value is in the key is in the map. And you can tell we have a table for the runtime. Our map, the intermap, is taken from the OCaml standard library. It's not written by ourselves. It's just like because we can compile any OCaml into JavaScript code. We can also compile OCaml standard library to JavaScript code. So it's taken from the OCaml standard library. And you see the performance is almost 3 times faster than the immutable.js library. And the good thing, because immutable map, our map, after the Google Closure compiler, in simple mode, you see the size is way, way more smaller than the JavaScript code, because we do a lot of data collamination. And even in the link time, we dedicate to the Google Closure data collamination. So we do different level of data collamination. In the module level, in the function level, we also do the purity analysis to analyze the code if it's pure and it's not used, and then we can just remove the code. And the other thing is, BuckleScript is compiled really, really fast. I mean, it's a truly fast compiler. A lot of compilers claim it's fast, but here is a snapshot. I mean, it's compiled the hello world example to native code for different language. S is for Scala. You can see for Scala, for code startup, it takes almost 5 seconds to compile hello world. And the K for the Qt is a language designed by JetBrains. It's a new JVM-based language. It takes like 3 seconds. For TypeScript, it's about 2 seconds. For the Hex, it's another language compiled JavaScript code. It takes about like the 0.1 seconds. But for OCaml, it's almost 20 milliseconds. I mean, 20 milliseconds. It's not like the 20% faster. It's like a magnitude faster than the other compilers. Another example I did with BuckleScript is we did a micro benchmark with the TypeScript. We have 2 modules. One module is define 500 Phoebe functions. The other module just call the Phoebe function 500 times. And you can see BuckleScript is almost take like 60 milliseconds to compile, and TypeScript takes more than 1 second. I mean, it's like almost 20 times faster than the TypeScript. And you can tell because the BuckleScript itself is compiled to JavaScript code. So you have the native backend, assembly backend, which is used in the benchmark. But you can also tell the the JavaScript backend, which means the compiler itself is compiled JavaScript code. And you can see how fast it is. Here the left side is the OCaml code, the right bottom is JavaScript code, and then every time we change the code in OCaml, we compile the JavaScript code, and then evolve the code in the top right panel. It's almost instant. There's no caching. Everything is done in the JavaScript backend. So I can say add A, see that it's almost instant. The compiler, the JavaScript backend compiler compiles OCaml code to JavaScript code, and then evolve the code. You see, there's no delay. Even for the JavaScript backend, the native backend is even more faster than the JavaScript backend. I mean, you can play with this, yeah. Yeah, I mean, but the performance is not our only goal. I mean, performance is good, but the other thing, we want to have a very expressive and efficient FFI to the JavaScript, because the language itself is nice, but it doesn't make sense if it doesn't have good story in interacting with the existing JavaScript code. So the FFI is divided in two parts. The first part is called OCaml from JavaScript code. The other is called JavaScript code from OCaml. So the good thing is all the OCaml itself is composed to two components. One is the ML file, which is the implementation. The other is MLI, which is the interface. It's like C++. You have a header file, you have a CPP file. So when we compile OCaml to JavaScript code, all the interface is respected. I mean, as long as it's exported in the MLI file, in the header file, it will be exported as the JavaScript module export dot. Here is example. Here for example, we remove some stuff just for. Here we see the export is because it's a playground. There's no ML file, but you see all the names are preserved. The interface is also respected. And also we have experimental support to also generate the TypeScript declaration files. So you can also call the OCaml from TypeScript. Another thing, we have built-in support for NPM. So you can publish your packages written in BuckleScript to NPM, and you can also consume the package from NPM, as long as you write the bindings. Here our BuckleScript is also published on the NPM. So if you want to try the BuckleScript, it's very easy. Just NPM install the BS platform. No dependency, just NPM install. And the good thing is we can reuse all the JavaScript ecosystem. For example, for any package published on the NPM, they provide for example, the Tonic. The Tonic is a cloud service. As long as you publish your package into NPM, they can host your JavaScript code, so you can try it on the fly. Because the OCaml code is compiled to idiomatic JavaScript code, you can try the OCaml standard library in JavaScript code. I can. So we can compile OCaml standard library to JavaScript code. This is the OCaml standard library documentation. And then we try to use the standard library, OCaml standard library in JavaScript platform. First, we import the array module. We evolve. And see all the array function, the function in array module is available in JavaScript library. Exactly the same as the OCaml standard library. You see the array module, for example, the concat, right? And you can see we have a concat here in OCaml standard library. So it's very easy to consume OCaml library just as JavaScript library. And now we import another library called the stream from the OCaml standard library. Okay, now we have two modules. And then we use the function concat from OCaml standard library, then convert. So here is the if you find the documentation in OCaml standard library in the stream module. There's a concat function which takes two arguments. One is string, is a separator. The other is a string list, and then generate a new string. It's like the JavaScript array.join in JavaScript code. So here we use the OCaml function, string.concat. First argument is a separator, and then give us a list. Then we run code. Let me refresh. You see, so so you can very easily to use the OCaml library as JavaScript library. This is a very good use case. For example, as we showed you before, we have some very highly efficient data structure. You don't need to do anything; just use it as JavaScript library. This is just one part of the FFI. The other part is called the JavaScript from OCaml. So it's just like TypeScript. You have to write types. Because in JavaScript, there's no types. So you have to write a type declaration for existing JavaScript libraries. And then you can call the JavaScript from OCaml. The good thing is OCaml is an extensible language. So OCaml has some extension and attributes. You can customize the language for the good FFI. And OCaml has a very expressive type system. So you can model different paradigms, like we have the struct typing. So it's very easy to model the JavaScript struct typing. It's like interface in TypeScript. And we also have the polymorph variant. It's very useful for the event handler. We'll show you later. And we also have like the other features. So basic syntax for the type declaration is write an external keyword. External is a keyword in OCaml, and give a name to the value, and give types. Then you can call it on the fly. Here's a very simple example. We want to write a binding to the math.exp. You first need to have a declare the exp function in OCaml and give it types. And then you can call it on the fly. I can show you using our playground. And this is generated code. You can see very easy to write the FFI, right? This is just a very simple example. So we have some more complex example. One highlight is OCaml is a carried language. So carried calling convention for every function it takes one argument and then return another function. But JavaScript is an uncarried language. So there's some semantics mismatch. This is the same thing in Haskell. Haskell is a carried language by default. So when you compile Haskell into JavaScript, every function is taking one argument. So we do a little customization. We introduce BS attributes. So if we want to use the uncarried calling convention, you just add the annotation BS, BuckleScript, means this function is uncarried. And then the compiler will do the arity checking. So if either you do the, oversupplied arguments or undersupplied arguments, the compiler will complain. This is very useful for the FFI because any JavaScript function is uncarried by default. So we provide a native uncarried calling convention. You can try it. Generate code. The other thing is in JavaScript code, this is not a good paradigm, but it's used everywhere, especially in the event handler. You have, for example, even in the React.js, in the callback, you have a list. This is depend on how it's called. We want to model this semantics precisely. So we also introduce another attribute called bs.list. So for bs.list, the first arguments will be compiled to as list. But you can also type it correctly. So here, array.map. Array.map in JavaScript code there's an implicit this argument. So to model this, faithfully, we have a bs.this attributes. You can see the generic code I can show you. So you see we write the type declaration for the array.map, which is a method. So we have an attribute called bs.send. This first argument is the object, and second argument and the rest argument is the arguments. So array.map take a callback. The callback has an implicit argument, which is this. So you can type this precisely. The second argument is you can customize this. So here we have the FFI can model the JavaScript, this semantics precise. Yeah, this is very important because for if you send an AJAX request using the XML HTTP request, it doesn't call back. We depend on this. So we have to give this a type. So we provide this native support in BuckleScript. Also in JavaScript, it's very, very common to have a string in the event handler or in the configuration, you have a list of strings. So to type this precisely, we support the string type and the interliteral type. In OCaml, it's called polymorphic variant. So here we want to write binding to read file sync in the node.js. And the encoding is basically an enumerated set of the strings. So either like UTF-8 or ASCII encoding and more. So we can type this precisely and compile to idiomatic JavaScript code. I can show you the generic JavaScript code. Because the FS is not available in the browser, so I should not evolve. So here you see we type the read file sync as first argument is a string, and second argument is a string type, either UTF-8 or ASCII. If I make mistake, write more 8, compiler will complain. And the good thing is the compiler also generates very readable idiomatic JavaScript code. Another thing, good thing with OCaml is support the labeled named argument. So you can give the argument a name. And if you reorder, here if you reorder the argument, it still works. And you make a typo, compiler will complain. Yeah, and also here if you want to bind a function from module, there's an attribute called bs.module. Then we compile, we require a module called fs from node.js core. Yeah, and we can add more encoding for like the Latin one, right? You can, you see, very useful. And we also support it's a string literal type. Even better is in node.js, there's a very common idiom paradigm. You have an event listener, event handler will give an event and have a callback. Right? This is very hard to type. In TypeScript, we just have a function, have interface, like say on event is a string, and have a callback is a function, because you cannot type precisely in TypeScript. And we do this in using a dependent type in OCaml, because the type of the second argument depends on the type of the first argument. And the first argument is like several events. So we want to write a binding to a read line, which is also a standard core of the node.js. The first argument is a bunch of events. And the second one is a callback. For example, in read line, there are two events, like line, close. For line, the function is string, is a from string to int. For close, the type signature of the callback is a unit to unit. So in this case, we can type this precisely in BuckleScript code. I can show you the. You see, we write the type, we write an abstract type because we don't care about the read line. Give a abstract type and write a signature on, which is given read line is an object because the method is a method. bs.send is a method, and the event is a line, and have a callback, close, another callback. Then we return a unit. Here we just register the read line. You can see it's very precise. And it also generates a very idiomatic OCaml JavaScript code. Here, if you make a mistake here, compile will complain because you write typo. This is very useful, and very powerful of the polymorph variant in OCaml. This feature is, so far as I know, polymorph variant is only available in OCaml. Yeah. And if you, here, because the callback is strong type, you will say string like the s+3, compile will complain because the callback for line is string, so you cannot add some value. Yeah. Another good thing with OCaml is we have the very good support for struct typing. Unlike Haskell, OCaml has very good support for the OO style. The name of OCaml is the objective camel, means it supports OO style natively. So the good thing with OO, because there are two kind of typing scheme. One is like the nominal typing, like C++. You have a class A, then you have a class B. Even they have that same field, that same method. You cannot reuse the code because they have different names. But in OCaml, it's not the same case. OCaml, as long as class A and class B share the same type, then you can reuse the code. This is very useful for the modeling JavaScript semantics because it's exactly the same as TypeScript for the struct typing. So here is the code. You can use the OCaml object code without declaring types. In BuckleScript, we use the double hash. The syntax is a bit weird, but I think you can get over it. The double hash is for the method dispatch. It's just like JavaScript dot. So you can see the F object. You see, no type declaration. You can just use the object, and we can use the code U equal F and create an object. Yeah, the syntax is a bit weird. I think you can get over it. So it's a JavaScript object. It's a white has and white. It's type checks. So if we make a typo here, it means type mismatch. The compiler will complain. This is different from nominal typing. In general, in Haskell, you have to declare type first before you use the record. But in OCaml, you don't need to do. You can just use it. Very like JavaScript. And if here we have, if we make a typo, also compile will also complain. And the good thing is it's extensible. So if you have more fields, like unused, compile will accept code because it's good enough. You have all the labels require this. And this, you can also make the JSON object type safe. You get so here we create a collection of the JSON objects, XS. So in OCaml, it arrays the bracket and the vertical bar. Syntax error. Oh yeah, I forgot the equal. Yeah. So here we create an array of the object, and then we have a new one. Syntax error. Oh yeah, you're right. You see you can write the OCaml code in a type safe way, and you make a typo in the collection. The compiler will complain because array in OCaml is a homogeneous type. So every object in the array have to be the same type. But the good thing we have tuple means you can write a heterogeneous. It's just like the Haskell tuple. Yeah, and then the other thing with array, if you make a write as a string, it also complain. So it's like very like the F# type provider. So in F#, if you give a JSON type, then you can write a compiler plugin to infer the type. in BuckleScript, I mean, you get this for free. The compiler will infer the JSON types for you. And the good thing with OCaml is we also support subtyping and the inheritance. This is not encouraged in OCaml style, but it's there. You can use it if you really want to use like class type. And we also support the inheritance. Here's an example. You can define a class type called title, and have a method called title, and have another type called class type widget. And this widget will inherit title. And then you can use the subtyping because widget inherit title. I mean, you have more method, right? I mean, you can do the subtyping, more do the UI stuff in OCaml. You have to write FFI. For example, you have to write the external create. For example, just say create widget. Because this depends on another module. Let me see. Oh, this is in the thing. You can only create class JavaScript class. Currently, the only way to create a JavaScript class is the JavaScript itself. OCaml doesn't support create a JavaScript class. It's for the FFI. But you can, yeah, that's the thing we want to improve later. We have issue in BuckleScript, I think. We eventually want to create a JavaScript class in OCaml, but currently the class is only for the FFI. But eventually we want to create a class in OCaml itself. Yeah, so I show you a lot of examples. There's another standalone example. It's the Node HTTP server, written in OCaml, compile the JavaScript code, and run in Node server. There's two modules. Basically, you write the HTTP types is a binding, and then can run code in a driver. Here is a binding. I mean, it's basically you write a. So for this simple example, we didn't care about the request type. We write the response is a JavaScript class, which means you can set the status code, and you have asked for the set header. End is also a response, because the end is a keyword in OCaml, so we add an underscore here. And the server, there is a JavaScript class, has a method called listen, with a port number, and the and string, and it has a callback. So to consume the JavaScript class, we have a attribute called bs.var of module, and then consume take a HTTP whole module as the OCaml value, which has the JavaScript class type. And this is a file to consume the bindings. The first part is just the normal OCaml code. You have a create server. This is a classic example from Node.js tutorial. You take the HTTP object and the create server, and have a callback, request, response. And you set the status code, set header, and end the request. And then you listen the port and host name. Then this is a function which doesn't depend on the JavaScript bindings. But eventually, you want to provide an HTTP object. The HTTP object is from the Node.js bindings will just show you. Yeah. The cool thing, you can see the general JavaScript code is just exact same as the OCaml code, very similar. I mean, line by line. Yeah. So the user can publish the code just to the NPM. So other people can use your OCaml library as a JavaScript library. As I showed you before, we also have a very nice integration with the reason. I mean, OCaml syntax is a little weird, but the Facebook the React.js team, they are working on improve the OCaml syntax. So we have also have a compiler in browser, compile reason to JavaScript code using BuckleScript. I can remove some code. I think maybe you will like this syntax a little better. I mean, it's the same code, but written in a maybe more syntax you like. Yeah. So we do a lot of optimizations. BuckleScript is not just a compiler, it's an optimizing compiler. We do the local code, invariant code motion, priority analysis, cross-module optimization, and constant folding, strength injection, and escape analysis. Actually, one example is the optimizing the carried calling convention. Because OCaml is a carried language. So in theory, you have to compile the function. Every function in OCaml has to be taken one argument, return another function. Actually, there are some language like PureScript that works this way. But this is highly inefficient because every time you create a new function, you have to allocate a closure. So we optimize, we do the arity analysis in the cross-module level. We analyze the arity of the function. So we can know in the compile time, know the function is either oversupplied or undersupplied. So here we have a function called fxyz, takes 3 arguments. Then we have another application, happens to take exact 3 arguments. Another application taking 2 arguments. In PureScript, you compile the function f, taking 1 argument, return another function, take another argument, return another function, and return another function. And then the application will apply the argument for 3 times. This is very bad for performance because every time you do the function generation or application, you have to pay for the performance. In BuckleScript, we do this arity inference in the cross-module level, so you can optimize this overhead. But we do more optimization than this. This is just one example. Excuse me, say again. Oh, that's uncarried calling convention. But for a function developer, like the Haskell or OCaml, you are getting used to the carried calling convention. It's more convenient. Carried calling convention means you can do a partial application. You can create a function, compose a function in a more convenient way. People like to write style in a carried calling convention. Haskell or OCaml or PureScript or Elm, they're all carried calling convention by default. But there's a mismatch, semantic mismatch between the Haskell or OCaml and the JavaScript code. So in BuckleScript, it allows you to write code in carried style, but again, you don't pay for the performance. For the FFI, the carried calling convention is for uncarried calling convention is most for the FFI, because the JavaScript code, every JavaScript function is uncarried by default. So you have to model the FFI faithfully. The only way to do it is you introduce the native uncarried calling convention. But if you write idiomatic OCaml code, you want to write it in carried style. Elm and PureScript and GHCJS are other typed ML-like language, which also generate the JavaScript code. It's very similar to Elm and PureScript. Elm doesn't generate readable code. Sorry, there's a typo. For PureScript, it generates readable code and also support some extensible record. PureScript is pure, but OCaml allows you to write the different style. You can write in imperative style and also OO style. The great thing about BuckleScript is it's not a new language. So you have assembly backend. You have different front end and different backends. So if you really want to the great performance, you can use a native backend, just like the compiler. We have a compiler, the BuckleScript compiler in both JavaScript backend and the assembly backend. But in the development mode, you want to get the fastest compiler. Then we compile BuckleScript into the assembly code, get the great performance. The other thing in Haskell is GHCJS. We compile the vanilla Haskell into JavaScript code. It's a whole program compiler, which means the GHCJS will take all your Haskell modules compile into a single monolithic JavaScript code. It's also, the reason with GHCJS is because in Haskell, it's a lazy language. So there's semantic mismatch. You really cannot generate very. But you have to have a linker, right? I mean, yeah. But every time you change the Haskell code, you have a comparison module and a linker the code. Yeah, we can. Yeah, so. Yeah, and pretty much so BuckleScript, yeah, the future work is more testing and more bindings to existing JavaScript libraries. One way is to reuse the TypeScript type declarations. So we can, in a semi-automatic way, to generate the type declaration from the TypeScript declaration to the OCaml FFI code. Another thing is a flow type checker, which is also written in OCaml. So we can reuse the flow, the Facebook flow compiler to generate a type declaration for the existing JavaScript libraries. And we want to work with them to provide better integration with the reason. Of course, the more optimization and documentation. Yeah. So that's pretty much what I want.